So that was all we had for image derivatives. Any question we have, we can take them now.
I
I have
wonder,
a,
go ahead.
so I have a question for you. Like, is the mask values arbitrary? The mask values for the x and y, the image mask that we have defined, like, are they like arbitrary one in the matrix for the f, x, and fy derivative masks?
This one?
Yeah, exactly. Is it like arbitrary one? Is it like defined by the how do you define those? The -1, 0, 1. Like, where do you get those from? That's my question.
So we discussed this backward difference, forward difference, central difference, right? And how
Yep.
this represents the derivative
Discrete
in one
derivative. Yep.
dimension.
Mhm.
And then we discussed like how we can represent that derivative using these masks.
Okay.
So the one I'm showing you for images, it's just like a simple extension of this one-dimensional mask,
Yep.
right? So those were
Understood.
extended using the central difference. So these are not arbitrary, these are like well designed.
Okay.
I just wonder why the central derivative still has the same effect as the backward and the forward. Because adding a zero, I just don't see why we have a central difference that has the same effect as the backward and forward.
No, central difference won't have the same effect. It's just like one way to compute derivative. I think I might have confused you. Backward difference and forward difference will have same kind of result. Central will definitely have different effect.
But they are
It's
all
just
they're all derivative, but they're just taking a different delta. Can I
right,
think that it
right.
down?
So yeah.
Okay.
So the
Um,
neighborhood on which they are operated is different. So of course, like the result will be different.
got it. And why you use the 3 by 3? Can we use 2 by 3, 1 by 3, or 4 by 3?
Yeah, you can have arbitrary shaped mask, and some of this has to do with like the efficiency, usually like in computer science, how things are implemented. If we have like symmetrical things, so that's one reason. Most of the kernels, when we do filtering, they are actually square shaped. And usually you will see like these are odd numbers, either 1 x 1, 3 x 3, or 5 x 5. Again, there is like some reasoning for that. For example, instead of 3 x 3, if we use a 2 x 2 kernel, right? So if you put at this location, then we don't know really like to which location that kernel belongs, right? For 3 x 3, we can clearly say that the center location is the one where we're interested in.
Then what about 2 by 3?
You can have 2 by 3 as well. Yeah, you can have 2 by 3. That's fine. But again, the issue will be like at which location you're focusing. You can't like concretely say that. You'll have to make some
Okay,
assumptions.
I see. I see. We need to have that center of the focus.
Yeah, and I'm not saying that's required, but that's like one reason you have odd numbers like in these kernels, 3 x 3, 5 x 5.
Okay.
Usually it makes things easier.
Why we choose the 1/3 as a to normalize instead of 1/9?
Yeah, I mean, you can have 1/9 as well. Uh, Again, that depends like what's your end goal. If essentially in this case, we are just measuring whether there is a difference or not, right? It's not that we are doing filtering and we are trying to preserve the structure of the image, which we will, for example, we were doing that in smoothing, right? So there it was really important you normalized it properly. Otherwise, the pixel values will shoot. In this case, we are only interested in extracting the edges. We'll talk about that later. So you can normalize with 1/9 as well.
So in that case, then we don't actually need normalize for having
True,
the.
that's true. That's true.
Okay,
Yeah.
okay, got it.
Okay, question from Zahin. What will be the mask for second derivative? Yeah, that's a good question. And for second derivative, you can take your one-dimensional derivative, right? And then maybe perform filtering using the second filter. That will give you the second order derivative, right? So we are going to come to that like when we talk about edges and Laplacian. Yeah, it won't be the same because if you use this filter, then it's just performing like a single step derivative, right? So ideally, you just perform that at like maybe 2 steps, so that second derivative, or you can merge the kernel first, get like the derivative mask for that. Okay. Now, any other question before we move on to the next lecture? Okay, so I think there's one more question. What happens when we use 2x2 matrix? You mean like as a filter? So if you are referring to like a 2x2 filter, I mean, you can just use those masks, right, which I showed you earlier, which were like -1 and 1. And if you extend that to two-dimensional, it will be like -1, 1, and again negative. You can just repeat those values. And the idea will be like, instead of placing 3x3 kernel, you will place 2x2 kernel, and you'll have to decide, okay, to which value that kernel belongs. And you can just make a judgment, pick any one of those up 4, and just keep repeating that process. Again, it will give you like edges in your input image. And of course, it will be different from like the kernel which we used. Okay. All right, so I think I don't see any other question. Okay. Let's go. All right, so any questions we have on the basics of edge detection?
So the purpose of the previous graph is just to show the accuracy of the recall and precision. Is that what the graph was? And it's just showing that like which algorithms have the best precision recall, like the performance rate. Is that what it is?
Yes, yeah, exactly. This is comparing the performance of different algorithms.
Mhm.
So if you are down here like completely 0, that's the worst algorithm.
Yep.
And if you are at this point where saying like your precision is also 1, your recall is also 1. So 1 is like the best number you can get for precision recall, right?
Mhm.
So that will be the best algorithm. And all these are like lying over here. And this is the human level performance.
Okay. So also I have a question. I'm going to look at the threshold-based segmentation, edge-based segmentation, but after we look at this edge detection, right? Isn't those two other methods apart from these?
Can you repeat that?
So like I'm saying, apart from these algorithms, isn't there an algorithm like the segmentation based algorithm for edge based segmentation, and then those kind of algorithms are there, right? They only apply for the image segmentation.
Yeah, I mean, segmentation, that's a different topic, right? We'll talk about segmentation as well. That will come way later. But there, you can say there is some connection, but right now we will not look into segmentation. That will be a separate topic altogether.
But we're going to see the edge detection there as well, right? In segmentation. Mm-hmm.
Segmentation, you can convert like your segmentation mask to edge detection, but really we won't make any connection there, like between edge detection and segmentation, because the goal is different there, right? Of course, I understand what you're trying to say. Like once you have the segmentation, that's kind of giving you the boundary, so that's close to edge detection. That's true. Okay.
Okay.
But we'll keep these two topics separate. Okay, question from Prithvi. Roof edge and step edge difference. So roof edge was your pixel intensity was actually increasing, and then it was suddenly coming down. So that was your roof edge. In real world example, you can say that like in a scene, let's say if you have a rope somewhere in between, so that rope will actually cause edge, right? But again, whatever you have in the background, the pixel value will suddenly change, and again the pixel value will go back to the background. So that will give you a roof edge. And step edge is like
my I
Yes, go
was
ahead.
gonna ask if there was if the roof edge was more like a step edge, like example, you on the left side of the image there's white white image, and then there's a slight difference, something like yeah. If you go ahead to the um, to the images example.
Oh, not this one?
No, after the next slide,
Okay.
the next one.
This one?
Yeah,
Yes.
to the last example. Last example.
This one?
Yeah, this one right here. So
Okay.
is this more of a roof edge or a step edge? Because here it starts with sort of gray, and then there's a white edge in between, and then there's sort of a different color. So
Yeah, so this you can say like as a step edge, and this is a step edge, and this you can model as a roof edge. Again, that depends on what kind of image resolution you are using and what kind of filter you are going to use, right? So let's say if your image resolution is too low, and there like this edge is just 1 or 2 pixels, so that can be a roof edge. But if it's a very high resolution video and just these width is like 100 or 200 pixels, then you can say, I mean, that could be a step edge as well.
okay,
So
so if it's a grayscale image, it doesn't matter. So it just and then okay, yeah, makes sense. Thank you.
okay, good. So I think there was one more question on chat. So Akshdeep is asking, in step edge, the change of intensity is abrupt. And in the roof edge, change of intensity is continuous. Yeah, I mean, that's not always like necessarily true. Even in roof edge, it could be like gradual. Right? Okay, so next question, Nasher, does the f and x correspond to f1 score? Okay, which slide f equals to x? Yeah, f1 score, we are not computing f1 score because I understand like where from where you're coming, like once you have a recall and precision, you can compute f1 score. But right now we are just looking at precision and recall, the way we are plotting that curve. Okay, so we are not computing f1 score here. So I don't know when you say f is equals to x. So which slide is that, Nashan? Okay, in the boundary detection graph. I see, I was just asking about the labels in that graph. Okay, this one. Oh, these values. Let me see. That's a good question. I never analyzed these. Yeah, if we of course we can compute f1 score, but if you look at these plot in f1 score, you will have then multiple f1 scores, right? So basically, this could be representing the maximum f1 score along this curve. Again, I will have to confirm that, but that's like one way you can just get one number to do the comparisons, right? So for example, if this is saying 0.9, so it could be like, let me see, it's saying 0.79, right? Yeah, this is the f1 score. This is the maximum f1 score of each of these plots. Because as you vary your threshold, you will have different precision, different recall. Then you can compute like f1 score for each of those. And this one over here is like the maximum one. Okay. Yeah, that's a good question.
Hi, Professor. I want to talk about the Gaussian filter a little bit. So, when you say that when we try to do the edge detection, we need to do the Gaussian filter first to smooth the the whole graph, you say the Gaussian filter actually emphasize the pixel itself, but I just wonder the no when the center of the kernel applies to the noise, should isn't that we also emphasize the noise pixel as well? Why the noise just gone after we apply the Gaussian kernel?
Okay, so first of all, I mean, Gaussian is just one way to smooth a pixel. Of course, you can use a box filter as well, and you will get like something similar result. So, but that's a separate issue. Now, to answer your question, so if you're applying the Gaussian kernel, so if you remember like from the last lecture, you are computing weighted average of all the neighboring pixels,
Ah, this average,
right? Yes. So it's
I
like weighted average, then whatever you have in the neighborhood, then it will give you some value. And then since you're sliding your kernel in like steps, that average value will not change that much.
Okay, it kind of compromise the noise, compensate the noise pixel, because surround when the noise happens, the surrounding will be the actual real pixel. Then when we average them, you kind of like compensate.
Right. That averaging is actually minimizing the effect of noise.
Okay. I also want to ask the when you can you move to the next slide? The DG, yes. Why we do the derivative of the Gaussian first, then um, is the order of the convolutional operation matters? I just
No, so
look. Mhm.
if you compute like, because Gaussian filter you know beforehand, right? So this is just one-time operation and you can use it.
Uh-huh.
But earlier, like if you perform this on image, mean your sample will change. Every location the values will change. So you'll have to compute that over and over again, right? But for Gaussian, it's the values for the Gaussian kernel is not going to change.
So the last graph means that the f congruence to the
Yes.
Gaussian derivative.
Yeah, the Gaussian derivative. Exactly.
Does the order matters if we use the Gaussian derivative convolute to the f versus compare with the f convolutes to the Gaussian derivative? Will that be different?
Okay, so convolution was commutative or not? It was commutative, right? So if you
Yeah.
compute derivative of this, and yeah, that's a good question. Yeah, I'm just thinking, because if you compute derivative of this noisy signal, then you're already losing the information about the signal itself, right? So the signal itself might be commutative, but when we are computing derivative, yeah, I will have to look into that, but I can sense that when it won't be the same thing, because as soon as you compute derivative of the signal, you are losing the signal, right? Then it doesn't matter whether you perform like smoothing on that signal or not. I will have to check that.
Okay.
I will post this in the announcement. So that's a good question.
Another question is why applying the derivative of the Gaussian convolutes to the function later still get the same result? Or can you explain why it works, just like you explained that why Gaussian works is because it emphasizes the center?
Right. So this one is actually this one will become more clear when we talk about the Laplacian filter, right? The second derivative. But I can quickly go over this.
Okay.
So if you look at this filter, so filtering is what? It's just pattern matching, right? If your kernel is actually matching the input signal, you will get a high response. That's true, right? That's one interpretation. Now, if you look at this signal, this is actually saying that your signal is going from positive to negative.
Yes.
Right. So this is called like zero crossing, when your signal actually crosses zero. And when we talk about like I think canny edge detection, there it will be more clear. but let me give you like the quick intuition on that. So whenever you have a zero crossing in your input signal, right? So this kernel will try to detect that. All
Okay.
right. And in this case, the zero crossing is happening just at this location. The value is actually going from very low value to a very high value,
Uh-huh.
right? And at all other places, like you will see, like it's the difference is very small, so it will just filter out those.
Oh, okay. So it kind of matching with the where the y value tries to goes to the zero, because
Right, right.
that's why the derivative of the Gaussian trying to match.
Yep.
Okay.
Okay.
Yeah. Last question. What do you mean the 3 pixel, 5 pixel when you talk about the smooth? The couple.
That's the size of the kernel, right? You can have a 1x1 kernel, 3x3, 2x2, or 5x5. That's
Okay.
like the neighborhood you're using for smoothing.
Got it.
All right. So any other question before we end? I think we are almost out of time. All right. So if no other question, we can end it here. Thank you.